the unit element S comma S, where S belongs to the multiplicative system S. Note that the definition of the multiplicative system has two conditions, right? But the first one is that the subset should not have 0, and the second one is that it has to be closed with respect to multiplication. But there is one more thing which we should not neglect, that is, in the beginning it is said that a multiplicative system is a non-empty set. So you will have something here, and using that you can create this unit element. So RS is a commutative ring with a unit element, that much is true. Okay, now comes the difficult part, the question of embedding. Can we always embed R into RS, just like we can embed D into F? And the answer is no. So to show that, we need a counterexample, and constructing that counterexample took me quite a while, like for example 1 or 2 months I took, and it just happened that I stumbled upon a convenient counterexample, because there is no definite way of finding something like that. So let us now show by an example that R is or R cannot be necessarily embedded in RS. So for this we are going to take the ring of integers modulo 6 for R equal to J6. According to the popular notation, people will write like this, but since Herstein is denoting the set of integers by J, so we stick to it. For R equal to this, and we need also a, okay, so J6 qualifies as a ring for our purpose. Why? Because the ring we took in this exercise, it is supposed to be a commutative ring with unit element. J6 is a commutative ring with unit element, so it's okay to take that. And what about the multiplicative system? It consists of these two equivalence classes, one having 2, the other having 4. Remember that these are equivalence or congruence classes, or rather I should say congruence classes modulo 6. You can verify that this is a multiplicative system. Okay, because if you multiply 2 with 2, you get 4. If you multiply 2 with 4, you get 8, which is nothing but 2 again. Okay, and if you multiply 4 with 4, then you get 16. 16 means so this is again 4. So the set is non-empty, it does not have the 0 element of R, and it is closed under multiplication. So that's why it's a multiplicative system. Okay, so for this two, we have Okay, the calculation of this one is not easy, or I mean, I should not say it's difficult, but it's time consuming. J6S, this ring, keep in mind that this ring will consist of equivalence classes the way we have defined, and it is nothing but this one is the equivalence class that has this ordered pair R comma S, where R is any element in the ring and S is coming from the multiplicative system. Okay, there are two more. One comma two, the equivalence class, and 2 comma 2. Okay, in brackets I would like to write something. One can verify that this equivalence class actually consists of these things. Zero comma 2, 0 comma 4, 3 comma 2, and 3 comma 4. Like that, this one consists of, it also has 4 ordered pairs, 1 comma 2, then 2 comma 4, then 4 comma 2, and 5 comma 4. And the last one, is 2 comma 2. It also has 4 ordered pairs, 1 comma 4, then 2 comma 2. 2 comma 2 has to be there because we are representing it by that, right? Then 4 comma 4, and finally 5 comma 2. Keep in mind that according to the definition of the equivalence relation we have in this exercise, any two ordered pairs in a single equivalence class are actually related. So I have in fact actually verified that this is related to this is related to this according to that definition. This is related to this, all of these are related, all of these are related, and all of these are related. And two ordered pairs coming from different equivalence classes are not related. One thing you can verify is that, do you remember the fundamental theorem of equivalence relation? Once we have an equivalence relation, then it partitions the set into disjoint equivalence classes. What is our set? Our set is M, and it consists of ordered pairs like this, where R is coming from J6 and S is coming from the multiplicative system. Now, since the multiplicative system has only two elements, 2 and 4, so you can see that every second coordinate is either 2 or 4. Now, do we have all the first coordinates? Let us see all the ordered pairs where the second coordinate is 2. 2 means congruence class 2. We have 0, 2, then we have 1, 2, then we have 2, 2, here we have 3, 2, and then here we have 4, 2, and finally 5, 2. So we actually have all the equivalent, all the ordered pairs that can be formed with 2 as the second coordinate. What about the ones having 4 as the second coordinate? 0, 4, then 1, 4, 2, 4, 3, 4, 4, 4, and finally 5, 4. And that actually exhausts all the possibilities. So if we can write this as this. Union 1, 2, union 2, 2. So M has been written as a union of non-empty disjoint equivalence classes. So this is our new ring J6S. Now, do you think J6 can be embedded in J6S? Because for that to happen, we have to have a mapping from J6 into J6S, that is an isomorphism. And according to the definition of an isomorphism, it's an injective or one-to-one mapping. Now J6 has 6 elements and J6S has 3 elements. So no matter how hard you try, you can never find an injective mapping that maps 6 elements into 3 elements, simply because here there are fewer elements. Whatever mapping you find, it can never be one-to-one. It has to be many-to-one. At least 2 elements should have, 2 different elements in J6 should have the same image. So that's why in this curious case, embedding is not possible. And that's what we are going to write. Since J6 has 6 elements and J6S has 3 elements, we cannot embed J6 into J6S. Okay, so it's not necessarily possible, but let me also give you one example where it is possible. Of course, we can embed J into Js, where S is equal to J minus 0. Keep in mind that J according to Herstein is the set of integers. So if we take that ring, because that is also a commutative ring with unit element, and S is the set of all non-zero elements. By the way, is this a multiplicative system in the ring of integers? Yes, it is non-empty, and it does not have the zero according to its definition, and product of any two non-zero integers is a non-zero integer. That means it is closed with respect to multiplication. So it's a non-zero, it's a multiplicative system, and it can be embedded. In this case, Js, the ring that we form, Js is actually nothing but the field of rational numbers. See how nice. The field of rational numbers. One more thing is there. Observe that in this case r comma s is related to r prime comma s prime if and only if r s prime is equal to r prime s. Okay, so in this particular case, the definition of this relation that we have in this exercise matches with the definition of the relation that we have in our actual theorem. So that's why we end up having not just a ring Rs or Js, but actually that becomes the field of quotients. So in this sense, you can say that this exercise gives us a construction which is more general than the field of quotients. In fact, this construction you will encounter when you study algebraic geometry, and there you study about a concept called localization. If time permits, we will see those things one day. So in this case, we really get an embedding. So it's not like we can never get an embedding. Okay, so this ends the complicated part C. Then we move on to part D, but I need ink. Okay, so D and E we are going to do together. So in D we were asked to show that the given function is a homomorphism, and we were asked to find the kernel, and in E we were asked to show that the kernel does not intersect the multiplicative system. To show that phi is a homomorphism one can follow the solution to exercise 3 above. Although in that solution we have written that we have already done it. It's because you see we have actually come across one such function from D into F, right, where we have defined it like this, where G was a non-zero element in D. We showed that this is an isomorphism. So the exact same thing will happen here. So that's why we are not doing it. We are just simply mentioning that it can be similarly done. Okay, now we come to the one more thing is this. Note that this we already noticed while solving that problem there, but we still write it once more, that the equivalence classes do not depend on the choice of this element S for all A belonging to R and S and S prime belonging to S. Oh, I said we have already noticed this. No, we noticed this in the context of theorem 361, but now our system is different because our second coordinates are coming from a multiplicative system, and the relation that we have in this exercise is also different. So we have to indeed note this separately. So that the function phi they defined is actually well defined. Okay, now we come to the question of kernel. So let A be any element in the kernel of phi, then the image of A under phi will be the zero element. So the image of A under phi is this, which is equal to the zero element, and this implies, if you go through the definition, A(s square S prime is equal to 0 for some S prime belonging to S. From this, one can see that the kernel is contained in this set X belonging to R such that Xs is equal to 0 for some S belonging to S, because that's what we are getting, right? S square S prime is an element in S because S is a multiplicative system, so it's closed under multiplication, and multiplying that by with A, we are getting 0. So the kernel is contained in this set. As a consequence, the kernel is disjoint with S. Why though? because if you see, if they had an element in common, then that element multiplied by some other element of S should have been 0. But since S is closed under multiplication, that product must be in S, which will mean that 0 is in S, contradicting the first condition of a multiplicative system. So that's why there can be no element in common and they are disjoint. So here we have completed D and E. And finally, we are left with part F. So part F is actually easy. For S1 and S2 belonging to S, we had to show that any elements of the form S1, S2 is invertible in the ring. One can verify that the inverse, multiplicative inverse, is just this. Just like our case of field of fractions. So here the solution ends. Now 2 more exercises are left. Let us just do them also at one go. Let D be an integral domain and A and B are 2 elements in D. Suppose that I like this exercise because it uses the field of fractions in a very clever and simple way. Suppose that A to the power n is equal to B to the power n and this for 2 relatively prime positive integers m and n. Okay, prove that A is equal to B. Okay, so if one of A or B is 0, then the other is also 0. Why? Because you see, if A is 0, the left hand side here is 0. That means B to the power n is equal to 0. Since we are in an integral domain, so if B is non-zero, then any positive power of B is also non-zero, from the fact that an integral domain has no zero divisor. So B to the power n being 0 would imply that B is also equal to 0. But in that case, we will have A and B both to be equal to 0, that is, they are equal. Similarly, if B is 0, then A is also 0. So assume that both A, B are non-zero. Okay, now let F be the field of quotients of D, which we know it will contain D in a sense, since M and N are relatively prime. So for relative primality we have that condition that an integer combination will be equal to 1. So there exists integers k and l such that km plus ln is equal to 1. Okay. Now we are going to do a calculation which will be in F, and that is mentioned here. The following computation is in F. Keeping in mind that the non-zero elements of F form a group under multiplication. And the computation is this: A is equal to a to the power 1, and this keep in mind it is an integral power of a group element, because you see now A and B, we have assumed both A and B are non-zero, so they belong to the integral domain. But since the integral domain can be embedded into the field, so they can be regarded as elements in the field, non-zero elements in the field. So they belong, both A and B belong to the group of non-zero field elements under multiplication, and because of that the integral powers of group elements and the laws of exponent, they can be applied here. That's why we need this. Now this one can be written as a to the power km plus ln, and using the laws of laws of exponent, I can write this as a to the power m whole to the power k times a to the power n whole to the power l. Now we apply these conditions. This is equal to b to the power m whole to the power k times b to the power n whole to the power l. So again we can write it as km plus ln, again applying the laws of exponents. This is b to the power 1, this is equal to b, and that's how we have a is equal to b. And we should also mention why we need the field. Of course we have used it, but what is the reason why do we need the field? Note that you see both m and n are positive integers, so at least one of k or l has to be, actually one of them will be positive, the other will be negative, because otherwise we cannot have this smallest positive integer. How will it be reduced? Note that either k is less than 0 or L is less than 0. To make sense of negative exponents, we need multiplicative inverses of non-zero elements. There the field F plays its role. So simply the fact that every integral domain is submerged inside a field helps us solve this problem. Otherwise, you can see, if you just simply write this, after that if you are thinking of integral domain, you cannot proceed like this, because k and L, any one of them may be negative and it loses meaning in the integral domain, but it has perfect meaning in the field which is outside the integral domain. And there is only one more exercise left.